the area of a triangle. Well, if you think about, we've already seen the area of a parallelogram, and I'm going to relate the area of a triangle to the area of a parallelogram. So this is a very similar style to what I did when I looked at figuring out the area of a trapezoid. So you'll notice there's a 1/2 in here, and that's kind of an indication of what I'm going to be doing. So let's call this side length A, B, and C. If I was to duplicate this triangle and kind of flip it over, and flip it around, I would end up with something that looks like this, where the B's line up with each other, the C flipped around and is over here, the A flipped over and is up here. So by doing this, this side would actually end up being parallel to that side, and this one would end up being parallel to that side. So I end up with a parallelogram. And we've already seen the area for a parallelogram is if you take the base, call one of these the base, and call this distance here measured at a perpendicular height. So if we were finding the area of the entire thing, the area total would be, let's call this H. This would be A times H. This side of the triangle I end up calling A. Usually in the formula we call it B for base, but the name of it isn't really that important. The important thing is that this one is measured at a perpendicular to, or this height is measured at a perpendicular to that base. That's a 90-degree angle. Alright, so that's the area of the total thing, but of course this is two triangles, so the area of the triangle would be 1/2 of this, or that divided by 2. And that's where we get this area equals 1/2 times 1/2 base times height. Because if we were to duplicate this, we'd end up with two triangles to get the area of a parallelogram, and then we could get the divide that by 2. In any case, so find the area of the following triangles. This triangle, we're given some additional measurements. We're given the 10 inches and 10.6 inches, but those ones I don't really care about, because all I care about is the base and the height. I know that this 13 is the base because it's measured at a perpendicular, or it is perpendicular to the height. So 1/2 the base times height, so 1/2 18, or 13 times 8, which gives me 52. This would be square inches. I could go about finding the perimeter as well. Looks like this is just asking me to find the area. Of course, the perimeter is just going to be the sum of the three sides. In this next example, you can see my height is measured kind of not vertically, it's this thing right here, which would force this one to be my base. So the area of this triangle is going to be 1/2 times base, that's 25, times height, which is 16, that is 200. These are all in centimeters, so we get 200 square centimeters. Alright, on this one, I have just enough to be able to do it. I have a height, and there's nothing saying that the height has to be on the inside of the triangle. It's perfectly fine for you to have the height being on the outside of the triangle like this. It just needs to be measured at a perpendicular to where this side would have gone if you were to extend it. That's why there's dashed lines here. So this is my height, this is my base. The area here is 1/2 times base times height. That's 120 square centimeters. So that's the area of a triangle if we have the base and the height. Heron's formula is actually a nice formula if we only have side lengths of a triangle. You can actually use Heron's formula to find the area of the triangle. None of the examples we see in this class will require Heron's formula, although the book does talk about it. I'm not sure why we don't have any examples that use it, that don't use it. Why we don't have any examples that use it. There we go. Now, in order to do Heron's formula, we actually use something called a semi-perimeter, which is what we get if we take and add together all the side lengths and divide by 2. We're just going to call that S for the moment, and then plug stuff into this formula. We do S times S minus A times S minus B times S minus C, multiply all that stuff together, take the square root of it, that will give us the area. So you could actually verify on some of these, if I wanted to use Heron's formula on this one, for instance. S is equal to, let's see, 10 plus 10.6 plus 13 divided by 2. Let's figure out what number that is. 10 plus 10.6 plus 13. Hit enter, divide by 2. I could have put that whole thing in parentheses and did divide by 2 in one line. I'm just choosing to do it this way. Get 16.8. That's my semi-perimeter. And so the area, I already found the area to be 52 square inches. Let's see if this gives us the same result, though. I'm actually curious. We get the square root of 16.8. That's the, I'm just plugging stuff into Heron's formula here. That's the S. Next I'll do S minus A. So 16.8 minus 10 times 16.8 minus 10.6 times 16.8 minus 13, which gives me 16 times parentheses 16.8 minus 10 times parentheses 16.8 minus 10.6 times 16.8 minus 13. Close that up. The product of all of these is that number. Let's take the square root of that. And we end up with, something that's not quite accurate. 50.6 approximately square inches. So what went wrong here? The area that I found here is 52 square inches. I think what went wrong here is these side lengths are probably, these were probably rounded fairly aggressively. I'm not sure exactly what side lengths would end up being here, but I'm going to attribute the error here in the fact that I'm basing it on the side lengths, which are not 100% accurate on this example.